Okay, good morning. Let's begin. So today we will begin chapter 6, which is frequency response. That's the final chapter. Estimated should take 3 classes, including today. So let's switch over to the notebook and talk about frequency response. So I mentioned this previously that electronic signals in the modern world are all around us, right? We are surrounded by electronic signals all around us. Whether they are wired or wireless, they work at a particular frequency. They're all time varying signals, meaning they have different values at any given point in time. And depending on how many cycles it completes in 1 second, well, that's how we describe the frequency. So we have talked about AM radio stations, FM radio stations. Broadcasting frequencies are basically the call sign of the radio station. Wireless routers run at 2.4 gigahertz, 5 gigahertz, right? If I just pull my cell phone out, that cell phone is receiving signals from AM radio stations, FM radio stations, television, satellite, AT&T, Verizon, T-Mobile. All the signals are going into the device, right? Then how does it not manage to, how does it work? Well, that happens because of the magic of filters. That is basically what we're going to study in this chapter. The title is frequency response, but basically what we're studying is electronic filters, basically circuits and how they respond to the frequencies of the incoming input signals. Okay. When I say incoming input signal, what I'm stating is, as an electronic device, the signals are present everywhere, right? Signals are present everywhere. So it's going into the device. Now, what the device does with the signal depends on the functionality of the device. If I wanted to, tune into a FM radio station, then there's a tuner and a filter in there that would tune only to that particular frequency, and so that is basically electronic filters. Okay. So far we have looked at circuits that have a source or multiple sources perhaps, and a few components, right? Typically the source is drawn on the left. So I just want to present a little slightly different manner of drawing the circuit, because that is what we will need going into this chapter. So let's say you have a circuit with a source, resistor, capacitor, and an inductor, right? So typical circuits we have seen, they look like this. Now, what if we isolate this, extend out the output, and we put the components inside a sealed box? Okay, we put the components inside a sealed box. Network basically is a synonym for circuits. You may have heard me talk about circuits and networks intermittently, right? So network in this instance simply refers to a circuit. So if you take all the components, put it inside a sealed box, we can say there is input on the left side, there's output on the right side. We don't care what is inside the box. We don't really care what the circuit actually does. Well, I mean, we care what it does, but we don't care how it does it. Okay. And we describe each of these terminals by a term known as port. P-O-R-T. P-O-R-T. On the left, we have the input port. On the right, we have the output port. Essentially, what I'm trying to say is we are looking at the same circuits. The structure is the same, everything is the same, but you're only going to look at it a little bit differently. You're going to combine the two terminals on each side of the circuit into what we call as a port. Okay, port. So each port has two terminals, plus and minus, and it has two ports, one input port and one output port. And so we call this as a two-terminal, two-port network. Two-terminal, two-port network. On the left, we have V in. On the right, we have V out. They're both functions of time, at least for now. right? In chapter 5, x-axis was always time. Going forward in this chapter, x-axis will always be frequency. And we will see that in just a little bit. Okay, but this is the representation that we will use, that we will be using for this chapter. Okay, so from that, we introduce another new term known as the transfer function. The transfer function for a particular network simply describes how the input is being transferred to the output. Hence the name transfer function. Okay, transfer function. Transfer function is a function of frequency. It's h of f. H of f. Simply put, h of f is the ratio of the output voltage to the input voltage. H of f is simply V out over V in. V out over V in. Okay. And what do you notice about the notation? It's not a function of time. It is a phasor. It's a complex quantity. So h of f is also a complex quantity represented by complex numbers. And thus h of f has magnitude and it has phase. It has magnitude and it has phase. And because it is a ratio of voltages, it is unitless. It doesn't have any units. Okay, so there are no units for h of f. Again, h of f is simply describing how the input is going to be transferred to the output. If this was an amplifier circuit, h of f would simply be describing the gain of the amplifier. Right? H of f would simply describe how the input's being transferred to the output. If it was an amplifier, it would just be describing the gain. When you give one volt input and you know what h of f is, then you can predict what the output is going to be. And that is why it is very important. It allows us to predict what the output of the circuit is going to be without knowing how the circuit is configured or without actually knowing what it's supposed to do. Okay. All we need to know to predict the output is h of f. So if we know h of f for a circuit, we can predict the output for any given input. If this h of f was an amplification gain of, let's say, 10, for instance, okay? Now, if I tell you V in is 1 volt, what is V out? 10 volts, right? H of f is V out over V in. So V out is H of f times V in. So H of f is known to us, 10 volts, 10. And V in is 1 volt, output is 10. If V in is 0.5, output is 5. And so on and so forth. Make sense? So in this entire chapter, we will take a look at filter circuits, and all of those filter circuits will have a particular description. The description would be the transfer function, H of f. Okay, H of f. So I just want to describe, I want to take this example right here and just show you how a filter might actually work. Okay. Input signals are an amalgamation of multiple different frequencies. Any time varying input signal can be represented as a sum of sinusoidal waveforms. We can take any incoming signal, doesn't matter what shape it is, and we can say that they're comprised all of sinusoidal waveforms. So in this particular example, there's only two. We have V in, and that V in signal has only two components. It only has two components. Again, it's a very simplistic example, very simplistic representation. This is not actually what a filter does. A filter does not actually split it up. This is just for explanation purposes. Okay, I want to be clear about that. Right here, I'm showing you that V in is being split up into two. That is not what a filter is actually doing. Okay, it's not splitting it up. This is just purely for the purposes of explanation. All right. So we take the incoming input signal and we can mathematically represent it as two separate sinusoidal signals. Okay, two separate sinusoidal signals. Call the one on the left as one on the right as two. Okay. Now, both of those are passed through this exact same circuit, but that circuit, depending on its transfer function, is going to affect each one of those differently. Signal number one is actually going to be amplified. So there is a gain that is imparted or increased in value to signal number one. Signal number two, on the other hand, is actually smaller and so is now attenuated. So on the left, we have amplification. Signal is amplified. On the right, it is attenuated. Amplification and attenuation are two sides of the same coin, antonyms of each other. In electronic circuits, this is a very common application. There are many signals where we want to amplify, and there are other signals that we want to attenuate, meaning reduce or increase in value. Okay, so a filter is amplifying one component while attenuating or blocking the other component. And then at the output, we combine that signal again. And we can compare how the output looks to the input. The smaller signal, I mean, not small signal, the big component actually is now reduced and it's gone. Okay, it's gone. So this is kind of again, as I said, it's a simplistic explanation for how a filter would work. Basically, a filter circuit will affect different components differently depending on the design of that circuit. Okay, depending on the design of the circuit, different components are affected differently. All right, any questions? Any questions at all? So let's look at an example. This example is also what the first homework in filter in this chapter is about. So this chapter has 3 homework assignments. It was actually only 1 homework assignment. Then a few years ago, I broke it up into 3. It only has like 1 or 2 problems, and all of them, and both problems I think are similar to this one. Okay. And then the last homework is resonant circuits, and resonant circuits again only has, I think it only has like 2. I may be mistaken, but I'll check. I think only has 2 problems. So they're not long. Anyway, so here we are given the graphical description of the transfer function of a particular circuit. We are not told what the circuit is. We are not told what it does. But we are asked to provide the output, V out of T. Okay, V out of T. So the graphical representation on the left here is the magnitude of H of F. In the right, it is the phase angle of H of F. Okay, so on the left, we have the magnitude. On the right, we have the phase. Now, we are simply asked to find the output given any particular input. Okay, given any particular input. We don't care what the circuit is. We don't care what it does. So let's take a look. And I'll go into this example right away. V in of T is given to us as 3 plus, let's see, plus 2 cos of 2000 pi T plus cos of 4000 pi t minus 70 degrees. Okay, that is V in of t, and we are asked to find V out of t. V out of t. Okay. So first thing, let's inspect. V in of t is comprised of 3 components. And those 3 components all have different frequencies. Right? Here we have 4000 pi. In the middle, we have 2000 pi. And the first component is basically a DC voltage. It doesn't even have a frequency. It's simply a constant value of 3. Right? If you represent this, it will simply be cos of 0. Right? Cos of 0t. F is equal to 0. So we cannot combine these 3 components. And if we cannot combine, we just find the individual answers and then leave the answer exactly the way the input is given to us as 3 separate components with simply a 3, whatever the value is, V in 1 plus V in 2 plus V in 3, and that's it. So that's the first thing that you should inspect, okay, whether the frequencies are the same or not. If they're not the same, we cannot supply, or we cannot subtract, or we cannot add these components. All right. So I'm going to break down V in of t into 3 separate components. I'm going to say V in 1 of t, V in 2 of t, and V in 3 of t. V in 1 is 3 volts. So frequency F is 0 hertz. V in 2 is 2 cos of 2000 pi t. If we compare it to the standard expression, Vm is equal to cos of omega t plus or minus theta. Vm is 2 volts. Omega is 2000 pi. Omega is 2 pi f. So f is omega divided by 2 pi. So f for this would be 2000 pi divided by 2 pi, which gives me f is equal to 1000 hertz. V in 3 is 4000 pi t minus 70 degrees. F is equal to 2000 hertz. Okay. So from chapter 5, V of t is Vm cos omega t plus or minus theta. We compare the expression to the standard expression of a time varying signal and extract information about the 3 quantities Vm, omega, and phase angle theta. Good so far, right? So now that we have the frequency information, we go over to our graphical charts or the plots that are provided to us. And we find the magnitude and the phase at each frequency. At 0, magnitude is 4, phase angle is 0. At 1000, magnitude is 3, phase angle is 30. At 2000, magnitude of 2, phase of 60. So I can write h of 0 is 4. H of 1000 has a magnitude of 3 and a phase of 30 degrees. And H of 2000 has a magnitude of 2 with a phase of 60. And that's why we don't really care what the circuit is or what it does. Okay. If we know the transfer function, we can predict what V out is going to be. We simply apply the equation V out is H of F times V in. And that's it. Now, each one of them is a complex quantity, so it's complex math. So I can write V out V out 1, this would be in phasor form, would be H of F. Actually, let's just write the generic expression. So V out is H of F times V in. So V out 1 is going to be H of F, meaning H of 0 times V in 1. This gives me 4 times 3, 12 volts. 12 volts. So there is a gain. There's a gain factor at 0 hertz. Okay. The circuit is amplifying the input signal if the input signal frequency is at 0 hertz, right? The incoming input signal was 3 volts. The output is now 12 volts. It's amplifying. Then V out 2 and V out 3, we'll do the same. This would be H of 1000 times V in 2. H of 1000 is 3 with an angle of 30. V in 2 is the phasor for V in 2 of T, magnitude of 2, phase angle 0. So 2 with a phase angle of 0. So V in 2 is 2, the phase angle 0, gives me 6, the phase angle of 30 volts, 30 degrees volts. And V out of 3 similarly. V out of 3 is H of 2000 times V in 3. This is 2 with an angle of 60 degrees times, what is V in of 3? Simply cos of 4000 pi t minus 70. So it's 1 minus 70. So it's 2 minus 10 volts. And that's it. That's the answer. As straightforward as that. So there's a gain inherent for all of them. The gain is just slightly different, right? For the first one, the gain is 4. For the second one, the gain is 3. The third one, the gain is 2, twice. And then beyond the frequency of 2500. So beyond 2500 hertz, everything is attenuated. Everything goes to 0. So if F was 2600, V out would be equal to 0. Any value greater than 2500. Because that's what the graphical plot shows us. All right, makes sense to everyone? Let's take 10 seconds or longer if you need. Think over it. Let me know if you have any questions. Any questions from anyone? Yes. Yeah. So the whole purpose is that if we know the transfer function, then we should be able to predict what the output is given any input. And so that would be, now this is a graphical representation of the transfer function. In the rest of the chapter, we'll have an analytical or an equation that is describing the transfer function. But the purpose, I mean, the procedure will be the same thing. So here we extracted H of F from the graphs and the charts that were given to us. The rest of the circuits, which is the filter circuits, the H of F is given to us, or we already know it because it's a low pass or high pass filter. We take the input, just plug it in there. That's going to be the last and final answer. So V out of T, right? Is that your question? Yes, that's going to be my last step. So because the question asked us to find V out of t, our final answer has to be in the time domain. It's V in 1 plus V out 1 plus V out 2. V out 2 would be magnitude 6 cos of 2000 pi t plus 30 degrees plus V out of 3, which is 2 cos of 4000 pi t minus 10 degrees. And the units for everything is volts. This would be your absolute final answer. Again, if it's asking you for the answer in time domain, you have to be, well, you have to recognize it and ensure that your final answer is in the time domain. Okay. So this is what the first homework is about. You would take the transfer function, the graphical representation, and predict what the output is. Yes. The frequency information? Yes, from the input. So right there. So the first step, we always want to take a look at the input components, equate omega is equal to 2 pi f, find the frequencies, and then we can proceed with the rest, because without this information, we cannot predict what it's going to do. All right, any other questions? Okay, then let's take a look at electronic filters. Now, we use the property of impedance, specifically of the capacitor and the inductor, to design our filter circuits. And the reason we can do that is because the behavior of a capacitor and inductor changes, or the impedance behavior changes as the frequency changes, right? Here, I have two columns, extremely low frequencies and extremely high frequencies. Basically, this refers to the frequencies of the incoming input signal. As the frequency f tends towards 0, it's representing extremely low frequencies. And extremely high frequencies, we are saying f tends towards infinity. And we know the equations for the impedance of an inductor and a capacitor. ZL is J 2 pi FL. F goes to 0. Inductor behaves like a short circuit. Chapter 3. If you apply DC voltage or current to an inductor at steady state, when it's fully charged, it behaves like a short circuit. F is equal to infinity. ZL is infinite. ZC is 1 over J 2 pi FC. When you apply DC voltage to a capacitor, meaning F is equal to 0, ZC is infinite. F tends towards infinity. ZC is 0. Or at least behaves like a short circuit. So based on these properties, we can model the capacitor and an inductor either with an open circuit or a short circuit. And I call this the handy dandy table, which allows me to analyze any circuit very quickly and efficiently. Okay, we can take a look at a circuit. We can model the behavior at extremely low and extremely high frequencies, replace the capacitor and inductor with its equivalent, open or short, and then see what it does to the output. Okay, and see what it does to the output. Make sense? Right. So the kinds of filters we're going to study. This table is a little misleading. It's not as if RC is only low pass and RL is only high pass. Okay, it's a 2 by 2 matrix. It's a 2 by 2 matrix. You can create RC low pass filters and RC high pass filters, and RL low pass and high pass. Okay, so in this chapter, what we're going to study is filters made out of capacitors and inductors, like circuits made out of capacitors and inductors. So if you have a single capacitor in the circuit, we have what is known as a RC filter or an RC circuit, right? Similar to what we saw in chapter 4. If you have an inductor, we call it a RL circuit. One energy storage element, first order differential equation, a first order circuit, and hence the name, a first order filter. So a single RC or single RL is a first order filter. And we can create both low pass as well as high pass filters using both RC and RL. So this in fact is a 2x2 cross matrix. Okay, there's actually 4 filters in there, 2 for RC and 2 for RL. If we combine both of these together, then we have what is known as the band pass or band reject filter. Okay, band pass or band reject or band stop. Most filters that we use in everyday life are a band pass filter. It allows a certain band of frequencies to pass through. In reality, of course, we only want one particular frequency to pass through, but real life, it can never work that way. If you want one single frequency to go through, there's going to be a certain band of frequencies on either side of that frequency that is going to pass through. Okay. So we're going to study 4 filters, 4 first order filters, and then a band pass and a band reject will have 2 energy storage elements. So it will be a second order filter. Okay, second order. So let's look at the first one of these, which is a RC low pass filter. RC low pass. Okay. The circuit essentially, now again, I'm not going to ask you for the derivation in the exam. Okay, that's not what I'm going to ask you. If you look at the circuit itself, what do you see? It's basically voltage source that represents, now we're going to put this in a sealed box, right? So V in on the left, and we have a resistor and capacitor in series on the right. And we simply have a voltage that is being applied to a resistor and capacitor in series. And that's it. That's what the circuit is. Okay, that is what the circuit is. You're taking the output across the capacitor. So V out is actually equal to VC. The derivation, well, there's not much to it. There's a derivation in the book, but simply put, if I was to draw the equivalent impedance circuit diagram for this circuit, I have 2 resistors in series or 2 impedances in series, ZC and R. I can either find the current in the circuit and then apply Ohm's law, or I can simply apply voltage division. And I can write V out is simply equal to V in times ZC over R plus ZC, right? One step answer. And then I take V in on the other side. I take V out over V in, which gives me the transfer function H of F for a RC low pass filter. And it turns out it has a standard form. H of F is 1 over 1 plus J F over FB. J, because again, it's a complex number, it's a complex quantity. Okay, H of F is 1 over 1 plus J F over FB. This expression is the same for all first order low pass filters, whether they are made out of RC or RL. Okay. In the next few slides, we will look at RL filters. RL filters also have the exact same expression for low pass. Yes.
What makes it low pass?
I will explain. We'll talk about that. Yeah. So we'll do a quick analysis using the handy dandy table, and we will see that it works as a low pass filter. So first the quantitative description, then we'll talk about qualitative. Yeah. So there is ZC is there, right? So it's a function of frequency in there, function of frequency. As if the function of frequency, sorry, function of frequency, meaning if the capacitor is seeing the incoming frequency, if the frequency is high, the impedance of the capacitor is going to be low. If the frequency is low, impedance is going to be high. And that's, that's how it's going to function as a low pass. So I'll talk about that. But let's talk about the equation first. Okay, 1 over 1 plus J F over FB. It's a complex quantity, so it has both magnitude and it has phase. The magnitude of H of F, and this equation is there in one of the last few slides, but essentially it's 1 over root of 1 plus F over FB square. Now, the equation describes the transfer function as a function of frequency, H of F. H of F, right? So F is the variable. F is the variable. The incoming input signal has multiple components, meaning the frequency is different for all components. So F is the variable. FB is a constant, and a circuit designer can choose FB depending on the values of R and C. And that FB stands for break frequency or it also stands for FC, the cutoff frequency. FB and FC are the same. Some books and some authors like to use FB. Some books you will see FC. They mean exactly the same thing. What it does, it's indicating the transition point. It's indicating the transition point. If you plot I'm going to say V out over here, but it may as well as be H or magnitude of H of F. Okay, magnitude of H of F. So x-axis will be frequency because now you're talking only in frequency. We want to predict the behavior of the circuit as a function of the frequency. So if FB was here, we are saying that all frequencies or all input components that have frequency less than FB will be allowed to pass through the circuit without any interruption, meaning the V out will be equal to V in. So all frequency values below FB should have a value that is equal to V in. Okay, if it's just H of F that's being plotted, it would just simply be 1. Okay, H of F is V out over V in. So V out is equal to V in, H of F is equal to 1. And hence all of these plots that you will see, if it's H of F or magnitude of H of F versus F, the highest value will always be 1. Okay, that is the point where V out is equal to V in. So all the way out to FB, the value will be equal to V in. Once the incoming input signal has a frequency component that is higher than FB, output drops to 0. Output drops to 0. So all frequencies below FB are allowed to pass through. All frequencies above are blocked. So this is also known as the pass band, and the other one is known as the blocked band. Now, this, of course, is showing you the graph of a ideal filter. FB is a hard transition. Anything less than FB has a value of Vn. Anything higher than FB has a value of 0. In real life, this transition is not that steep. It's not a sudden transition. It's a very slow transition. Like this. So this is ideal. And this would be a real life filter. FB is somewhere here, obviously, depending on the design. And the way it would relate to the equation is at F is equal to FB, H of F will have a value of 1 over root 2. V out or V in will be 1 over root 2. Okay, H of F will have a value of 1 over, or magnitude of H of F will have a value of 1 over root 2, which comes out to be 0.707, 70%. So in real life, at FB, the value of the output will drop to 70% of the input, 0.707. That is the transition point in a real life filter. Okay, the difference is versus a ideal filter is that at FB, on either side of FB, the value of that frequency is not so maximum. If it's less, if it's FB minus 1 hertz, the value is not 100%. It's only going to be 70% higher, slightly higher than 70%. And if you do FB plus 1, meaning on the right side of FB, it does not go all the way to 0. It'll just be about 70% or slightly lower, right? So we still get some value coming out at the output. But in real life filters, that's what it is. Especially a first order filter will have a slope that looks like this. A higher order filter will have a much sharper slope that approximates the ideal filter. Okay, that approximates the ideal filter. So that is the mathematical part of it, mathematical equation. Let's use the handy dandy table and analyze the circuit. So at F is equal to 0, meaning extremely low frequencies, what happens? Capacitor is, what is the capacitor? Open. The capacitor is open. What is V out? You have a voltage, you have a resistor in series, terminals are open. V out is equal to V in. So low frequencies, as F tends towards 0, low frequencies are allowed to pass. So this is allowed to pass through. So by using that table, you have to see what the value of V out is. If V out is equal to V in, then it's allowing those frequencies to pass through. If V out is equal to 0, then those are said to be blocked. So high frequencies, what happens? As F tends towards infinity, capacitor behaves like a short circuit. It's behaving like a short circuit. Everything is flowing through the resistor back into the circuit. V out is taken across the same terminals of the capacitor. So V out is equal to 0 volts. If V out is 0, then high frequencies are blocked. And thus the circuit works as a low pass filter. Low pass filter. Okay. Does that make sense? Again, it's a quick and easy analysis. But if you wanted to do it mathematically, you can plug in multiple values of F So F is less than FB. So if FB is, let's say, 1,000, you plug in F is equal to 1, 10, 100. And you can see it does not change the magnitude of the output. Magnitude of the output is only going to change after FB, after F goes higher than FB. So then it starts reducing. But again, using the handy dandy table, we can analyze any circuit quickly and efficiently. FB is a constant, which is 1 over 2 pi RC. And that is going to remain the same whether you have a RC filter that is a low pass or a high pass. Okay, we will see that in the next few slides. All right, questions? Any questions at all? Any questions? Okay, I'm going to end class here today. We'll pick up here again on Monday, look at the other remaining 3 filters. There's a homework due. I don't know when it is, but I'll make sure I'll make it due like Sunday night. So if it's due like tomorrow, I'll push it back to Sunday. But that first homework in this chapter has to deal with the graphical representation of the transfer function. So it shouldn't take very long to get done. Final quiz on Monday, which is quiz 7, deals with AC power. So I'm announcing in class right now, AC power. Most likely I will not have power factor correction, but I haven't completely finalized it yet. So I will send an email and I'll post it later on. But again, AC power analysis Monday, last and final quiz of the quarter. All right, have a good weekend, and I will see you all on Monday.